All right, guys, welcome to week 10. Hopefully everyone's exam 2 went well. I'll have those grades up by Wednesday, as I usually do. But right now, let's jump right into lab 8, and we're going to be looking at stream discharge today. So there's streams, rivers, and tributaries. A stream is a body of water with a current confined within a bed and stream banks. River is a large natural stream flowing in a well-defined channel to the sea, a lake, or another stream. Sorry, that's a typo right there. Let's see if we could just, let's go back. Yeah, so that's just, that's a typo, that's C, or another stream. And then lastly, a tributary is a river of a stream flowing into a large stream, river, or lake. All right, so all three of these have something called a watershed, and a watershed is also known as a basin, drainage area, catchment. A watershed is a land area where all water drains to the same particular discharge point. So this would be like the mouth of the Mississippi River, right? That drains into the ocean from the Mississippi River in New Orleans. It's bounded hydraulically. It is divided by topography, and watersheds affect all living things. So watersheds are influenced primarily by topography of a given areas. As water flows downhill, gravity causes water to flow downhill. So this is a nice diagram of what a watershed would look like. So from the mountains all the way to the estuary, and then the estuary. An estuary is where the mouth of a river mixes with the salty ocean water. So discharge. So today's lab is primarily going to focus on calculating discharge of a stream. And discharge is the volume of water flowing across a certain distance in a stream per second. And it is, go ahead and annotate here. This is the formula we're going to be working with today. Make sure you take note of Q is equal to A times V. And in this formula, Q is equal to discharge. And then the unit of measurement will be using, it could be either one of these two, but the one we'll primarily be looking at today is meters cubed divided by seconds. And the A in this formula is area of the channel cross section. So if you're looking at a stream, how far is it across? And that's the width times depth in order to get the area. And then the V is the water velocity in units of distance over time. So how fast and how far is this water moving over a certain amount of time? All right, let's move to the next one. So first we're going to look at how to measure area. So the A in the formula, Q is equal to A times V. So it is, let me go ahead and get my annotation tool out again. It is area is equal to width times depth. Width is constant because you just measure how far it is across at one point in the stream, but depth is not constant. It could change. The stream could be deeper in one location versus another. So what hydrolysis do is they divide them into cross sections. So if you look down here, you could see there's different cross sections. They did that for the depth, so they can get an average depth. So once you divide them into cross sections, you average all the depths of the cross section to get your average. This average will be the depth you used in this formula. So once again, once you get the width and the depth, you multiply them to get the area, and then you'll plug that area into this formula, the final formula on the lab. So let's do a quick example together, right? We did these cross sections, so you will do 1.8 plus 2 plus 4 plus 6 plus 4 plus 3.6 plus 3.4 plus 2.8. And once you add all those together, since there's 1, 2, 3, 4, 5, 6, 7, 8, let me double check. 1, 2, 3, 4, 5, 6, 7, 8. You divide them by 8, and that will be your that will be your average depth. And that will be the depth you use when you do width times depth is equal to A. So now that once we get the average depth, we'll plug it into the D, and then we have the 0 and the 20. So the width is 20 times average depth, and that equals the area of the stream. That's how you're going to calculate A for the Q is equal to A times V formula. All right, now let's figure out how to calculate the V, right? There's two parts of this formula. So stream velocity. Velocity is the distance traveled by an object in a given amount of time. The units we're going to use are meters per second or feet per second. It'll be meters per second in the lab. And there's two different measuring techniques, the float method and the flow meter method. Just for your general knowledge and how you could do it out in the field. As you probably know, we will not be going out to the field. We won't be able to conduct an experiment hands-on with this, unfortunately. So the flow meter method, you use a weighting rod and a velocity sensor. There's a little cup at the end, you can see it. The faster the cup spins, the greater the velocity. This means the stream is flowing at a faster pace. When the velocity is lower, that means the stream is moving slower. And this is a nice little diagram of the float method of estimating flow. So you start, let me go ahead and get my annotations out. What color should I use for this? Probably red or maybe pink. So you start, you have this float. You started at this line that you've measured. So these people did 10 feet. And this is your point where you measure, this is your starting line, ending line. You'll put it in the stream or the river, your float, and you'll take the time of how long it takes to get from the start to the end point. And once you do that, you'll do it 3 to 5 to 10 times, and then average out the float to estimate the float of the river, the velocity of it using the float method. In this lab, we will be getting numbers, we'll be getting data from 5 different times and averaging them out. So you put the float at the start point, at the end point, calculate how many seconds it takes to get from start to end, do that a few times, and then average it out to get your velocity. All right, now measuring velocity. It's not constant along the entire width nor depth of the channel. Regarding width, the stream flows the fastest, so the greatest velocity, at the center while it flows the slowest on the bank, so the sides of the stream. Regarding the depth, the stream flows the fastest at the top of the water and the slowest at the bottom. It flows slowest at the bottom because of the friction with the ground and with the stuff that is at the bottom of a stream. All right, now let's look into the procedure to measure velocity. So you'd get a tape measure along the channel to get the width. You'd set up measurements at every distance. So example, every 2 meters, and then you use the flow meter to determine velocity at each point. A way to do this, since once again, velocity is not constant for the width nor the depth, there's the 6/10 rule. This is the average velocity of the said stream is found at 6/10 depth from the top. So an example of that would be 5 meters depth is the measure at 5 meters depth. If the stream was that deep, the measurement of velocity at 3 meters would be the average. So the way we found this is 5 times 6 over 10, so 6/10, and that's equal to the 3 meters. So we use that 6/10 rules to find the place we should do the measurement for the velocity, and that'll give us the average. Before we go on, I do want you to take note right here of this graph. So this graph is the distance below the surface relative to the velocity of the stream. There is going to be a question on your lab that asks if it's a linear or nonlinear relationship. This is where you come to for that answer. Remember, linear means a straight line. Nonlinear is anything but a straight line. So I'll let you take that hint and do with it what you want to. All right, let's move on and calculate some velocity. Okay, so what affects stream discharge? Different factors can. Climate, a high PET, like we did a week or two ago. It's more evaporation, there's less discharge water, right? There's less water to go out into the drainage area. The bigger the drainage area, the there tends to be a higher discharge. Usually, this isn't always the case. And this isn't always the case for also many different regions. Vegetation on the banks of a stream, so somewhere with more plant life, the higher density of that vegetation, the less discharge will be. The plants need the water. The plants take the water and, use it to grow and keep themselves alive. Human activities also alter the stream discharge. Dams severely alter discharge of a watershed. Dams will completely stop at some places and flood it other places. That's why there's been so many environmental battles over dams in all parts of the world. Agriculture uses a lot of water and also dries out the soil, uses a lot of the material and the matter in the soil. So it could be either a good or a bad thing. It's usually a bad thing in the case of large-scale agriculture. And then urbanization, it reduces the amount of water that can infiltrate the soil or the ground. The more blacktop or concrete there is, that water doesn't soak into the ground and won't make it to a stream or to an underwater aquifer. And so this would be the stream we would have been looking at for the experiment, Scripps Cottage stream on campus. So, and then for part 2 of the experiment, you don't need a graph. You'll be given data and it looks a lot like something you're gonna have to graph. Don't graph it. Just read over that paragraph really carefully, look at the data, digest it. And the hypothesis I'm giving to you as discharge Q increases with increasing drainage area. The hypothesis is going to be as discharge increases, so the Q and our Q is equal to V times A, so will the drainage area. So they have a positive relationship. As one increases, so does the other. And this image may be helpful. It's one of the drainage areas you're examining in part 2 of the lab. This is part 1 of this week. I'm going to go over some examples really quickly, and I'm going to use the actual lab. So you'll have some of the answers there. I'm going to explain how I've given the data and how to calculate some means and steps to take. So this is part 1. Please do tune in to part 2 of the videos for this week so you can get a better idea of how to apply this information to lab.